Hi everybody, we're gonna get started here. Welcome back to Chem 131. We're gonna finish chapter 13 today. I have no idea if this is updating. It says that there's only like 3 people here so far. I'm not starting like 30 minutes early or something, am I? No, it's 12. Okay. So anyway, we're gonna get started here. Yesterday was the lab lecture. I know somebody asked me, like, where is it? Why is it not online? And I know that YouTube was taking its time yesterday to process videos, so if that happens again, um, the videos are there. It's just that sometimes it takes a while for it to be visible on the channel. You can always go digging through the playlists, and those have the videos in them too. Sometimes those update earlier, so look for them there too. I believe this is where we left off, where we were talking about these substituents of benzene and also these substituents of benzene. These are going to be common enough that you're going to want to memorize these. Now, the previous page, some of them, like chlorobenzene or bromobenzene or iodobenzene or whatever, like those are just going to be the groups that are attached to them. And for a lot of these, just knowing whatever the group is good enough. These specific 4 here, we don't call something methylbenzene. We call it toluene. We don't call something hydroxybenzene. We call it phenol. And so on and so forth. So these 4 specifically will appear later on. So make sure that you know these names well enough that you have an idea of what the molecule look like. In the lab that you're going to do on week, I want to say it's week 6. It's the 3rd lab. You're going to have to find some of these functional groups on structures of molecules, so you'll need to know that too. Now, the benzene ring itself can actually serve as a group. So just like you can have a methyl group or an ethyl group or a chloro group or whatever, you can have a phenyl group. A phenyl group is when you have the benzene ring come off the main chain. So if I was drawing a chain of carbons, something like this, and I had to make it long enough so I can go down here and use this space, I could then put a benzene ring like this and have it attached to the main chain. So this would be 1, 2, 3, 4, 5. Sorry, I counted and then wrote the number that I was counting. 1, 2, 3, 4, 8. Wait, that's not how you guys count. So this would be 2-phenyl. I can't spell. I was gonna put heptane, but that's not 8. 2-phenyl octane. Okay? If you see a long chain and you see a benzene ring in it, and it's just sort of branched off of that chain as if it were a group, treat it as a group. The benzene doesn't have to be the focus of the attention, and if it's not the focus of attention, then it's called a phenyl group. Now, here's some more examples of molecules that you can name. Since this molecule right here is a 7-carbon chain, and the branch occurs at position 4, and the group is a phenyl group, 4-phenylheptane seems like a good name for it. Remember that when we're naming cyclic hydrocarbons, we would name the groups by counting around such that I have the lowest possible numbers, and both groups look like they're phenyl groups, so we'll just call it that, 1,3-diphenyl cyclohexane. Will always be at the end of a double bond. It has to be by definition because this double bond has to either be on this side or it would be on the other sides in the other spaces. So that is just a feature of what the result will be. But yeah, it'll always touch a double bond, but specifically a double bond in a benzene ring. So it's more appropriate to say that it's just touching a benzene ring. Sorry, I gotta drink my water here. And ignore the cat in the hallway. Now, when we have compounds with two groups attached, you could name the groups and number them like normal, but there are also alternative naming methods to try and identify these a little more concisely. And so what we do is we sort of imagine that our benzene ring is a clock with one of the groups at the 12 o'clock position, and then the other groups land wherever they do. And then we have terms to assign to where these groups fall apart relative to each other. If two groups are one space apart, that is, something's on 1 and something's on 2, the term that we use for this is called ortho. If they're 2 spaces apart... Oh my goodness. Get out of here. Kresnik wants to go outside, even though it's like 27 degrees out. He just sat there and yelled in my face. We have 2 spaces apart for our groups that we call the meta. And if we have 3 spaces apart, or what I just say on opposite sides, then these are called para. And so the abbreviations that are used for these are just the first letters of those words. So ortho is just you put a little O in front and then name what it is. Meta is you put an M in front, and P is you put a P. Para is you put a P in the front. So for each of these, I have written just the generic name, and then instead of saying 1,2-dichlorobenzene, you could also write O-dichlorobenzene to say, oh, they are 1 space apart. Or you could write M-dichlorobenzene, and that would indicate that they were 2 spaces apart. They were meta. Now, these do not need to be the same group to use this designation. I've just used the same group for simplicity's sake. But if I go to the preview problem window here, we could do all sorts of names here. So, for example, if I wanted to do this molecule like this, so I could do this. Now, you'll notice that nothing is at 12 o'clock, so I could rotate it around in such a way that this one was up here and then this was over here. Or I could just count how many spaces between these there are. So there are 2 spaces apart. And so this would be meta. And then I just named the groups alphabetically. So this would be bromo, chloro, benzene. And of course, you put the groups alphabetically like we've been doing all along. What if you had something like this, though? If I look at what this is one of those funky special benzenes that I asked you to name before. You remember this name, hopefully. Now, the groups themselves are 3 spaces apart, so we would call that para. Chlorophenol. And so you could see how this sort of melding of common names with the IUPAC system can be convenient, but it's also kind of frustrating because it's like, oh, now we have this other side project to learn for names. And yeah, we kind of do. So these are a naming scheme that is so common that we use these a lot of the time with substituted benzene rings. So it's worth knowing them. Let's do one more example here. So I'll go like this. We'll put this over here. And I'll put that there. So how far apart are they? And then what is this thing? So they are one space apart. So I would call this ortho, iodo, benzoic acid. So remember, you are not constrained to having two groups that are the same. They can be any two groups you want, including the stuff that is on the other page. So you could have aniline involved, you could have whatever really. All right. What happens if you have more than two groups? If you have more than two groups, you cannot do ortho, meta, and para because those orientations only describe two groups. So if you have three, then we just start listing off all the groups. Now on the left here, this is an example of IUPAC versus this common meta, ortho, para scheming. Either of those names is accepted as correct. So just be on the lookout for ortho, meta, and para possibilities. I may ask you to recognize like which groups are ortho, or what's the name of this molecule, and only use ortho, meta, and para, and etc. Then if we have only, or not only, if we have more than two groups, so three or more, then I just start numbering them in the way that we've been doing all along. So over here, I would have to number them this way to get the lowest numbering. So I'd have 1, 2, 4 trichlorobenzene. Over here, I would have to number them. Obviously, it's going to be like 1, 3, 5. But I need to put the 1 in the position that is first alphabetically because it's always going to be 1, 3, 5. So this would be the answer here. 1 bromo, 3 chloro, 5 iodobenzene. All right. I'm going to put some groups on the screen here for you to name. Give me the name of these aromatic compounds, and in about 4 minutes, we'll come back and go over the answers. See you in a bit. How are we doing? Once you get names for these, go ahead and type them in the chat. That's correct, yeah. Either of those names works, but be able to recognize both of them. Yeah, it should have difluorobenzene. Oops, I read it and my brain filled it in there too. What about these other two funky ones? What's the central group here? Yeah, be careful, because benzyne is not a thing that we will encounter in this class. I think benzyne is like a very, very specific thing that happens to like a very certain reaction. I remember that from college. I'm like, oh yeah. But we'll never see it in this class. Like it's not a common thing. Let's go over the answers here. So 1, 2, 3, 4. I could number either way going around here. 1, 4 difluoro benzene. Or, since they're across from each other, para fluoroben. I meant to put difluorobenzene. There you go. For this second one, everything is coming off of the 1 position on the benzene ring here. But it would be easier to describe this instead as a cyclobutane. So I'm going to number the groups. So I've got iodo and then phenyl. This comes first alphabetically. So this would be 1 iodo, 3 phenyl, cyclobutane. Now, very important, you can only use ortho, meta, and para for benzene. Okay? So, just because these two things are opposite each other does not make them para, because they're also not 3 groups apart. Or 3 spaces apart, I should say. So we only use ortho, meta, and para for benzene rings, not any other of the cyclo groups. Otherwise, I would have already introduced them to you, right? All right, over here, I've got 1, 2, 3, 4, 5, 6. I got a hexane. I've got a phenyl. I got a phenyl. So this molecule over here would be 3,4-diphenyl hexane. Because the group that's coming off right here is the phenyl group. It does look kind of like a toluene, but be careful. Excuse me. Oh my goodness, it's cold in my office here. Let me turn on the heater real quick. All right, so that's how we name aromatic compounds. Let me know if you have any questions. This next section is just a sort of, hey, these are things that exist. So if you put a bunch of benzenes together, like say 2 of them, like this, it's called a polycyclic aromatic compound. Polycyclic just means there are many rings that are fused together. Now, in a polycyclic aromatic compound, all of the rings have double bonds everywhere that they can. Ooh, excuse me. But you do not draw a line in every position, because if I drew a line here where I'm putting it in yellow, both those carbons in the middle would have 5 bonds, so I can't do that. So the structure is drawn in such a way that all of the carbons shown have 4 bonds connecting them all together. And you could put as many of these rings together as you want. If you have 2 rings fused together like this, actually it doesn't matter which orientation, you could put it up here or whatever, and it would be symmetric if it was just 2. 2 of those rings fused together is called naphthalene. Naphthalene is a compound that was used in mothballs. So if you ever smelled mothballs as a kid in like the 80s or 90s or whatever, and you're like, oh, that has a weird smell. Yeah, it was naphthalene. There are other common polycyclic compounds, but you will not need to memorize them. All you really need to know is that polycyclic aromatic compounds are bad. Why are they bad? Well, they react in very weird ways, because putting a bunch of benzene rings together actually makes them more reactive, it turns out. And so polycyclic compounds in the body are often carcinogens. And the most common places to find them are through things that undergo incomplete combustion. So burning wood, or burning plant matter such as tobacco smoke, burning fuel. Whenever you undergo incomplete combustion, what ends up typically happening is that you just get random assortments of molecules. And depending on what your fuel source is, if it's gasoline, you're not likely to get a lot of benzene out of that, but it can happen. You could get some benzene rings fused together. Things like tobacco smoke comes from tobacco, which is a plant. Plants have aromatic compounds in them, so it's not very difficult for those to just still be around after combustion when it's incomplete, and then maybe fuse together with other benzene rings to make weird stuff. Now, because aromatic compounds are aromatic, this is why you get the different smells for when you burn things. So burnt wood has a particular smell to it, and what you're smelling are probably aromatic compounds. Tobacco smoke has a particular smell to it. Gasoline exhaust has a particular smell to it. And usually what those smells are from very small concentrations of specific compounds. Most of them that have unique smells are polycyclic aromatics. I think that's everything I have for the chapter. So, polycyclic aromatics exist. They're toxic. Don't breathe them. Hooray. Now, what else can we do with aromatic compounds? Aromatic compounds can't be made by your body. The human body does not have the correct enzymes to produce its own aromatic compounds, but sometimes they are useful in very specific vitamins. So one specific such vitamin is vitamin B2. So anything that has a benzene ring in it that you need has to come from elsewhere. And so you need to consume vitamin B2 from various sources. Besides the biochemistry, we use other aromatic compounds for solvents and synthesis and stuff like that. So polystyrene, which is a polymer, it looks like this. So I'll just draw polystyrene really quickly. So if I have styrene, which is this, and I worked with styrene as a grad student. Actually, if I had styrene was bad for me. It meant my reaction didn't work. But if I take styrene and I react it with another styrene, and it doesn't matter that my double bonds are in the wrong spots. Don't worry about that. Remember that to make a polymer, I remove the double bond and then attach it to the next carbon over here. And I can remove this double bond and attach it to the next carbon over here. And this will just keep happening over and over and over and over and over. And so that's polystyrene. As you can see, that's super nonpolar. Like, it's full of benzene rings, full of phenyl groups. And it will not dissolve in something like, say, water, which is very polar. So polystyrene cups or plastic bags or whatever are a very useful polymer for keeping water where it needs to be, which is generally in a specific spot or out of other things. But also, those compounds are very, very stable and won't dissolve or biodegrade over time. So that could be a consequence that we should consider. All right. I think that's it for chapter 13. Hooray. I forgot your little sound effect here, so hold on. There we go. Hooray! Alright, screen's gonna go black for a second while I get the next chapter up. Which time is it? It's only 12:30. Open. That's not what I want. That sent me to the desktop, and I have to dig through folders. There we go, we'll do it this way. Alright. Chapter 14 is very long. Because when I hit the spacebar, you're going to see the topics just go off the screen. And when I was writing this slide, or these slides, I was like, when does it end? Ah! But a lot of these sections are actually really short. So what we're going to do in this chapter is we're going to discuss 3 principal types of molecules. We're going to talk about alcohols. Hooray, we finally can talk about booze. Yay! Alcohols are one of the most common functional groups. So common that you generally, after finishing Chem 131, you will likely enjoy alcohols. One specific alcohol. I should be more clear. We're going to talk about their properties. We're going to talk about phenol a little bit more in its own section. Then we're going to talk about ethers, which are basically worthless. Ethers are not very exciting. Then we're going to talk about aldehydes and ketones, which are actually quite reactive and quite common. And let me squirt gun a cat. No, please. My cats are misbehaving this morning. They really want to go outside, you guys. Want to go outside. It's so cold. What we're going to do is, before we actually get to all those functional groups, aldehydes, ketones, alcohols, etc., I'm going to just show you all the functional groups we're going to talk about in this class on the next slide. So, a functional group is any part of a molecule that has a specific function to it. And what that function would be is that it can react in some way under the correct conditions. So, for example, in the last section, we talked all about alkenes and alkynes. Those are functional groups. When you have a double bond present under the correct conditions, such as, say, H2 and platinum are present, or Br2 is present, it'll react. Something that would not be a functional group would be an alkane. Alkanes just don't really do anything at all. They just sit there. Alright, so here is the list of all of the functional groups that we care about in this class. And we have seen the alkene, the alkyne, we've seen a benzene ring or a phenyl group, and we've seen alkyl halides. Yeah, we've done 3 weeks of class and we've only seen 4 of the possible. I don't know how many there are there. 13? And this isn't even the entire list of them. This is just what we're going to cover in this class. There are far, far more of these. So, just as a heads up, let's talk about where we're going to see these while you look at these and consider them. So, we're going to talk about alcohols, ethers. Are thiols in this chapter? They must be. Aldehydes and ketones. So, this is all this chapter. We're going to talk about these here. I don't think we do esters because we do ester hydrolysis in the next chapter. So we're going to do all this in this chapter. And then we're going to do these. Oops, that's the wrong pen. We're going to do these ones right here in chapter 15. And then we're done with OChem, believe it or not. Wow, that is really faint and I don't like it, but that's okay. There we go. So after this chapter and then chapter 15, we're done with organic chemistry and we'll move on to biochemistry. The biochem chapters are a lot shorter, but they're more complicated. So, all right. Your job is going to be to look at a molecule and find its functional groups and then tell me what those functional groups can do based on the reactions we've studied. So, for example, if I showed you a random molecule that had a double bond in it, you would immediately want to circle that double bond and then say, oh, this would react with hydrogen and a catalyst, or it would react with HX, where X is a halogen, or it would react with H2O if sulfuric acid is present, and so on and so forth. So that's the level of knowledge that I want you to have, is that you can look at a molecule and go, oh, these are the functional groups, and these are the reactions that affect those functional groups. Typically speaking, molecules tend to be very selective, and you won't have the same reactants do different reactions to a molecule. But that's not always true. We're going to look at one specific example in this chapter, where if we heat something in the presence of sulfuric acid, we get 2 different results depending on how hot we heat it. But for the most part, if you do a reaction, it will affect the targeted functional group. Okay. The other thing I want to mention on these diagrams here, so this squiggly line here is just the rest of the hydrocarbons chain. So the squiggly line means I am attached to the main chain at this point somewhere. Sometimes you see the letter R. And what R means is that R represents any combination of C's or H's that you want it to be. And so the reason that you might list R would just be to say, like, okay, maybe they're both phenyl groups, and I don't want to draw 2 phenyl rings. So I would write NR2, and then underneath I would write R equals pH for phenyl, or something like that. So if you see R, just think, oh, it's a bunch of carbons and hydrogens. Nearly all of these functional groups are polar. Nearly all of these functional groups interact with other things that are polar. Some of them may hydrogen bond. So, for example, this fluoro group right here would hydrogen bond. This amine would hydrogen bond. Alcohols and ethers hydrogen bond. All of these down here hydrogen bond. Now, whether they are hydrogen bond donors or acceptors or both depends on their structure. So if this amine has this hydrogen here, then this would be a hydrogen bond donor and an acceptor. But if it had only R groups, it would only be an acceptor. Ethers can only be acceptors because they don't have hydrogens attached to this oxygen. But if I had water come up to it like this, it could accept the hydrogen bond like that. And so that affects solubility. Things that can hydrogen bond to themselves affect their boiling points, and so on and so forth. All right. Down here, I have cholesterol. This is the molecule cholesterol. There are only two functional groups that you really care about, and you've probably already found them. So type them in the chat what the two functional group names are once you found them. All right, we found the alkene. So there it is. Whoop. Actually, let me do that in a different color. All right, there's our alkene. What's the other functional group? I mean, clearly it's this thing, right? What is this called? So it is a hydroxyl group, but what functional group would that be called? Like, what does hydroxyl mean? Is it like an ester? Is it a amine? Like, what is it? Alcohol, there you go. Now, what about the rest of the molecule? Is there anything important going on here? Well, it turns out that this is just a specific structure, excuse me, that exists, but the rest of the cholesterol molecule itself does not do any sort of chemistry with its surroundings, unless the surroundings are like specifically enzymes. Now, you might notice that, oh, there's a lot of C's and H's here. So what you would expect cholesterol to be, so cholesterol should be insoluble in water, which it very much is. And it should tend to stick together because because all of this is just dispersion, right? It's all nonpolar. And so it would attract to other molecules that are also nonpolar. And so cholesterol molecules tend to clump together, which is particularly bad if the place they clump together is your arteries. However, that said, cholesterol being in a place like your arteries might not be a bad thing if, for example, your arteries underwent, like, I don't know, like there was a cut or abrasion in the wall of the artery and then blood could get out of the artery. That would obviously be very bad. But if you would put cholesterol molecules in the way, those cholesterol molecules are hydrophobic, and so water could not pass between them. And so you could effectively use cholesterol to plug a hole in, say, an artery. A hole in, like, the artery wall. So the left functional group is the alcohol. That's right. So this is my alcohol. And this is my alkene. Everything else that is circled with up here, this is just a alkane. And remember, the alkanes are not functional groups. They're just sort of the default template. Okay, that's functional groups. So when we come back, actually, do I want to start talking about alcohols? Yeah, let's do a little bit of talk about alcohols before we take our break. Because we could go 10 more minutes before we take a break. All right, so now what we're going to do, we're going to talk about just alcohols for the next, probably the rest of the lecture. We're going to talk about all the things that you can do with alcohols, and that'll probably be good for today. So, alcohols are really common. Perhaps you're drinking alcohol right now. I don't know, maybe it's like later in the day, and you're sitting down to watch the video, and you have a glass of wine or something, or vodka, whatever. I don't judge. I drink it all too. The OH group, which is the OH functional group that we care about for alcohols, is called the hydroxyl group, which you guys already identified because you've read ahead, so sweet. You know where we're going with this. So I may refer to these as hydroxyl groups. I may just refer to them as OHs because it's easy to just say OH. If you write a molecule in a line angle structure, the OH needs to occur in this order. So, for example, this would be okay to write, but this would not be okay. Because what this implies is that my carbon that's here is bonded to this H, which is then bonded to this O. So instead what we would do here is we'd flip them around. And you saw this on the previous slide. So this is still an OH group. We always put the O attached to the carbon, and then the H is attached to the O. Okay? And it has to go in that order, depending on whatever orientation you were looking at. If you put the H on the other side all the time, and you just, like, maybe you're really a fan of Santa, and you just want to write ho, ho, ho everywhere, and you do this, that's fine. What's not okay for this situation up above, though, would be to go like this. See the difference? It's subtle, but there is a difference there. And we want to make sure that we are always implying that the carbon bond is between a carbon and an oxygen and not a hydrogen for the hydroxyl group. So this is incorrect, but this one's correct. All right, here's two examples of alcohols. This is ethanol. Ethanol is the alcohol that we consume to enjoy ourselves and loosen up socially. At a technical level, what you are doing when you consume ethanol is you are poisoning yourself because your body does not know what to do with ethanol, so it sends it to the liver, and your liver tries to oxidize it. And so it turns ethyl alcohol into acetaldehyde. Acetaldehyde is the hangover molecule. And then if it oxidizes that further, it becomes acetic acid, which is just vinegar. Vinegar is very soluble in water because it has all these oxygens on it. It's very easy to remove from the body, and so then you can pass it through your urine, presumably. I just know what the molecules become. I don't actually know their biochemical pathway, but I would assume that that is the fate of ethanol. But since you are requiring your liver to do that to get rid of it from your body because it shouldn't be there, you were technically poisoning yourself. So enjoy your poison. That's where the expression choose your poison comes from. When you go to a bar and, like, the bartender or whatever is a pirate, I guess. Arr, choose your poison, matey. Down here we have phenol. Phenol is just the alcohol of benzene. Phenols are kind of neat. We use them as disinfectants, and they're mildly acidic. So they basically clean stuff. Pick your poison, choose your poison, whatever, right? That's close enough. I've actually heard both. All right, how do you name alcohols? Alcohols are really easy to name. We're going to name them in a similar way to how we name... It says alkanes here. I would say alkenes is probably more appropriate. But what you're going to do is you're going to number the longest chain that has the alcohol in it. And then just do everything else the same. The only thing that you're going to change is the very end. Instead of ending it with, like, cyclohexane, you would add all. So it'd be like cyclohexanol. Now, you do have to number the position of the alcohol. And so you're going to put that number in the same place where you would put an alkene. So like how we had 2-butene, you could have 2-butanol. Or maybe you have 3-methyl-2-butanol, for example. Stuff like that. We're going to see a bunch of examples, and you're going to see that, oh, this is very similar. So naming these molecules shouldn't be too hard. So let's do some examples here. Well, what I call this alcohol. So first I have to find the longest chain, but remember I have to have the alcohol involved in the chain. So if your first instinct is, oh, this must be 1, 2, 3, 4, 5, 6, that actually doesn't work because my alcohol is not involved in the chain there. So I have to use this, which means I have to have this carbon involved in the chain. So the longest chain is actually a pentane. Okay, so be careful. You're going to have this. That's the same issue that comes up when you're talking about double bonds is you have to include the double bond or triple bond in the chain. Same thing here. You have to include the alcohol. Then we're going to number it so that the alcohol has the lowest possible number. And so that means we're going to number it this way. And then we name stuff. So what is this? Hopefully everybody's looking at that and going ethyl. I don't know who ethyl is, but she keeps showing up in our molecules. And then we have the alcohol here. And so we would just name this based on what we see. So we have a 2-ethyl, 1, and then there were 5 carbons, so this would be a pentanol. There you go. Be careful that you don't accidentally count this as part of the chain. It's not. It is a group off the chain. All right, let's name some more alcohols. What would I call this one? I'm going to let you try this one on your own. Type in the name in the chat when you think you have the answer. All right, we have all sorts of answers here. So we need to find the longest chain that it contains the alcohol. So this carbon contains my alcohol, so I have to pass through it, which means that I need to include that carbon in my longest chain. Everybody's going with butanol, huh? But if I keep the chain going, so here's 4, I could just keep going over here. 5, 6, 7, right? So there is a 7-carbon chain that includes the alcohol carbon on it. And now I want to number this so that I have the smallest number in front of the alcohol. So if I go this way, or if I go this way, well, that's interesting. I have 4 for alcohol in both directions. So then I would start numbering them so that the other groups have the smallest possible numbers. Well, going this way I had a 2, and going this way I had a 3 as the first group. So the correct numbering would be from right to left here. Because not only is my OH at the lowest possible group, all other numbers are also as small as possible. Then I need to name the groups that are coming off of this, and so I have a methyl and a methyl. So this would be 2,5-dimethyl, 4-heptanol. So the challenge is going to be find that longest chain. Remember, you want the longest chain that you can make that also includes the alcohol. Yeah, it doesn't have to be in position 1. It can be anywhere on the chain you want, but you want the lowest possible number. Because if you had to put the alcohol at position 1, you would have all sorts of crazy side groups for everything. Because then everything would functionally be a side group, so... All right, let's give you... let's give you this next slide before we go on to the examples, apparently. I forgot about this slide. Okay. There is an alternative naming scheme that is also IUPAC, and I sort of hate this. Because why would we teach you this specific naming scheme and then say, oh, here's a second one? So this is the naming scheme we're going to use in this class, the one that's in yellow here. But there is a second naming scheme that exists where we move the number in front of the all to indicate where the alcohol is. So we're going to use this one. And that this one exists, but you can ignore it. The only reason that I'm introducing this to you is because other materials are going to have this nomenclature, and so I do want you to have at least seen it. I will not test you on the second naming scheme. I will point out its importance, though. So the reason that this second naming scheme exists is because when molecules get more complex, this naming scheme becomes more flexible. For example, if you had a double bond and an alcohol, how do you name both? Because we've been changing the ending, right? Well, I only have one ending. I can either make it heptanol or heptene, but I can't do both, right? And instead, what ends up happening is you get like 4-hept, 2-ene, 3-ol, or whatever. You're going to see that on this example. Here you go. So here are some ridiculous examples that this is beyond the scope of what we're going to be naming. But you can see that, okay, let's find the longest chain here. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Wait a second. 1, 2, 3, 4, 5, 6. I just can't count. Okay, so what I've highlighted has 8 carbons. So this would be position 1. This would be position 2. So 4-ethyl, that's pretty easy. And then you'll see that what ends up going on here is instead of saying 2-octene 1-octanol or something like that. We write oct because it is an 8-carbon chain. And then 2-ene is this right here. And then 1-ol is this right here. Yes, it looks really stupid, doesn't it? Same thing here. So here's our carbon chain. So this one is a pentane. So 1, 2, 3, 4, 5. That would be our longest chain. I want the alcohols or alkenes to have the lowest possible number. So this becomes 2. Sorry, because this has to be 1. And then I would name it as appropriate. So this would be 2-ol. Here's my 3-ene. And then 5,5-dibromo. So the only reason that I'm showing you this naming scheme is just to let you know this exists and this is why. We're not going to do molecules this complicated. So I'm not going to give you any molecules that have double bonds and alcohols together. We're just going to do one or the other because I have enough stuff to test you on. Don't worry about it. All right, someone would like to say something before we take a break. There you go. What would you like to say? Hi. Hi. Maya says, please enjoy your break for 10 minutes. Oops, that's the wrong slide. That is 10 minutes that you could pet Maya. But you can't pet Maya because she's right here. So I will have to bear the burden and pet her myself. So we're gonna start the clock. We'll put on more Earthbound music, and I'll see you in a bit. Meow, 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 meow. That's what Maya says. She came back. She followed me out of the room and left for a bit, and then now she's back. Hi, Maya, what do you want? Maya, do you want to say hi again? You want to say hi? She says, take another 10-minute break. No, we can't do that. No. We have to get back to work, because we have to name more alcohols. So... Oh, here we go. Yeah, name more alcohols. So remember, you are looking for the longest chain that contains the alcohol. I've tried to hide it in some of these structures. I'm trying not to laugh because Maya's making little chirpy noises. It's kind of breaking my concentration. So find the longest chain, number the carbon so that the lowest number is at the carbon with the alcohol, and then you're in good shape. Okay, so go ahead and name these, and I'm going to continue to pet the cat because she won't go away. Alright, I went and put the cats in another room so that they wouldn't bug me. And by put, I mean I put them in the bedroom and then walked away, and then they left the bedroom. So, and the other cat came in here and was like, "I want you to pay attention to me too." So I was petting him, and then when I went to sit down, he ran up and jumped in my chair because cats, right? So I sat on him. Now he's upset with me. Maya's not upset with me, but Kresnik, my other cat, not super happy. Let's go over the answers. You should not sit on your cats, because it's always your fault. All right, find the longest chain that has the alcohol. So there's my alcohol. So I have to use this carbon. So I'm going to go 1, 2, 3, 4, 5. And then up looks longer. So we'll go 6, 7, 8. And so then this would be, here's an ethyl. 5 ethyl. 3 octanol. There you go. And that's what's popping up in the chat, so that's good. How about down here? What's the longest chain? Well, it's a cyclohexane. So we're going to put the number 1 position over here for the hydroxy group. I could go that way, or I could go the other way and get to 3. I don't know why I started numbering that way. But yeah, that's totally right. So 3-methyl, 1 cyclohexanol. Now that I think about it, I don't know if that 1 is actually necessary, to be honest. Let me find that in the notes real quick. I'm just trying something. 3-methyl. I cannot type. So, because this OH group right here, this can only ever be at position 1, right? So we don't even need that 1 in there. So we could just write 3-methyl cyclohexanol. On this one over here, let's count this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay. So there's my longest chain, so I can't select the thing. There we go. So this is phenyl. 1, 2, 3 is propyl. 1, 2, 3, 4, 5, 6. pH is before PR, so this would be 5 phenyl. 2 propyl. I'm going to run out of space here. 1 hexanol. Good. All right, we are in good shape. We can name alcohols. Now, what happens when you have more than one alcohol to name? If you have 2 alcohols present, then we have to give it a different name. If you have 3 present, you would give it a different name, and so on. For the 3-methyl cyclohexanol, since OH is at position 1, and it's always going to be at position 1 because that's how we number it, right? For something that is just an alcohol, you would not need to put the 1 there. All right. If you have 2 alcohols present, we're going to call it a diol. So 2 hydroxides, diol. 3 hydroxides, triol. 4 would be tetrol, and so on and so forth. Now, we're going to name these the same way, but instead of saying hexanol, what we're going to do is we're just going to add diol to the end of the hydrocarbon name. So this would be, for example, this would be 1 OH group on hexane. But if I had 2 OH groups, then it would be a hexane diol instead of a hexanol. So we keep the extra letters at the end of the entire alkane chain, and then you just write diol, or triol, or whatever you want to put in there. So, for example, this molecule here, what's the longest carbon chain? It's 2 carbons long. So I would say 1, 2, ethane diol. That should be an N. But all right, what else can we do with these? The reason that we care about multiple OH groups is because there's going to be a really common molecule that we see later on called glycerol. Glycerol is 1,2,3 propane triol. What would this be called? I'm going to let you try this one real quick. So number the longest chain, and then give it a name. So it's really close. So let's number longest chain. So 1, 2, 3, 4, 5. That includes all of the carbons that have OHs on them. So we got a methyl here. That would be 3-methyl, 2,4 pentane diol. So the di goes in front of the ol, and there you go. All right, so I'm going to give you more of these to try. Here you go. Name these diols and trials. This one over here this is our glycerol on the left here. We'll talk more about glycerol in a second. All right, 1 or 2 more minutes and we'll go over the answers. I think most people have these figured out. All right, let's go over the answers. So I'm going to start over here on this left one. So this is glycerol. We're going to talk about glycerol again later on in the chapter. 1, 2, 3. 1, 2, 3. Propane and propane accessories trial. All right. The one on the right is also easy. So 1, 2, 3, 4, 5 is my cyclopentane here. This one I do need to number because there are 2 positions. And so this would be 1, 3 cyclopentane diol. And then down here, I gotta find the longest chain, but it has to go through both of them. So this is gonna start here. 1, 2, 3, 4, 5, 6 is looks like a hexane. So 1, 2, 3, 4. I have to go that way. So all right. So that would be my groups would be at 2, 3, 4, and 5. It doesn't matter which direction I go. Both my OHs are going to be at 2 and 5. So I want ethyl to be the next one alphabetically. So this is the correct numbering method. So this would be 3 ethyl, 4 methyl, 2, 5 hexane diol. Sorry, my N's do not come out correct. All right, very good. We can name alcohols. All right, any questions, let me know. Let's move on to the next section. Oh, there's one more thing we got to talk about for alcohols. So we got to talk about primary, secondary, and tertiary. So later on, we're going to talk about how alcohols react based on their classification. We're going to classify alcohols right here as primary, secondary, or tertiary based on the type of carbon that it's attached to. And so what we're going to do is we're going to look at our OH and we're going to say, okay, the carbon that I'm bonded to, how many carbons is it bonded to? And so a primary alcohol is attached to a carbon that's on the end of a chain. In other words, this carbon is only connected to one other carbon. A secondary carbon would be a carbon attached to 2 other carbons. So here's my hydroxide. I'm going to look at this carbon. How many carbons is it attached to? 2. And then finally, a tertiary would be, okay, my hydroxide is attached to a carbon that is attached to 3 other carbons. And so that would look like this. So here's my hydroxide. I'm going to look at this carbon. How many carbons is it attached to? 1, 2, 3. Now, looking at this, you should be able to tell, just on sight, which ones are primary, which ones are secondary, and which ones are tertiary, because they look very different. So if I go to this, that's not right. There we go. And I draw like this. There we go. A primary alcohol will go straight on the end there. So that would be primary. A secondary would go on one of the middle ones. So this would be a secondary. I can't write. And then if I had something like that, that would be tertiary. We do have abbreviations for writing primary, secondary, and tertiary, and they are this. So 1 with a degree symbol, 2 with a degree symbol, and 3 with a degree symbol. So you're going to see that shorthand come up quite often. So let's look at some more carbons and see if we can identify them, because we're going to need to do that eventually. So for each alcohol on these structures, I want you to try this first before I jump in and give you the answers here. Label which carbons are which, primary, secondary, or tertiary. And so in each case, you're going to be looking at the carbon that the hydroxide group is attached to. And so I'm going to indicate those in red. And then tell me, just going left to right, what you think the answers are. You should be able to do that in a minute. Oh, I got distracted on my phone. I apologize. All right, let's count the carbons that are attached to things here. Let me get a different color out here. Let's do light blue. There we go. All right. So here's the carbon in question. So here's 1 carbon, 2 carbons. So this would be a secondary alcohol. Here is my carbon. It is connected to 1 other carbon. Now, even though it says R, remember that R could be any other hydrocarbon. And so even if this is like a benzene or whatever, there's still only 1 carbon attached to this carbon. And so this would be primary. And then this one down here, 1, 2, 3 carbons attached to my central carbon. So that is tertiary. So it looks like everybody can identify these by sight. So that's great. All right. Keep this in mind because when we get to aldehydes and ketones, it'll be important. All right, let's do one more section today. Let's talk about physical properties of alcohols. And then we'll do reactions on tomorrow. All right. Alcohols have the OH group, which makes them polar. So, oops, I didn't actually mean to tap the pad there. So, if I draw in the electrons, these guys are not just polar, they're capable of hydrogen bonding. So, let's go like this. What this means is that if I have a second ethanol molecule here, I could make a hydrogen bonding interaction like that. And so ethanol molecules will interact with each other, but they'll also interact with water because instead of having the ethanol part over here, I could just go boop. And water could interact with this, so the same thing. So since I can interact with water easily, that means that alcohols are soluble in water. So not only will alcohols dissolve in water and mix, which is why when you have beer or vodka or whatever, you don't have like a layer of ethanol at the bottom or the top. It mixes completely. Now, here's a question though. What if I tried to do this? So here's my alcohol. And then water comes along and looks at this. And you might say, well, okay, I could interact with this tiny part of the molecule, but what about this long hydrocarbon chain that's going on? This is all nonpolar. Will this dissolve in water? Hopefully you remember the solubility lab from, excuse me, 121. Whereas the carbon chain gets longer, the solubility goes down. So alcohols will be soluble, but if you make the nonpolar part too long, it becomes insoluble again. Okay, so there is a limit to how soluble alcohols can be. Now, as far as their boiling point is concerned, when you stick an OH group on there, this OH group can hydrogen bond to another OH group like we showed on the previous slide. And when it does that, those molecules stick together much more strongly. So the boiling point of butane is negative 1 degree Celsius. If you have like a butane lighter or you have like that butane fuel and you spray it accidentally on like a counter or whatever, it evaporates like crazy fast because it boils at negative 1 Celsius. 1 propanol, which has about the same mass, I just replaced the C here with an O. Its boiling point is way higher because it can hydrogen bond to itself. Butane only has dispersion. Propanol has hydrogen bonding. Things with hydrogen bonding stick to each other much more strongly and thus will not boil unless you heat them up much more. So as we go through... Oh my goodness, I'm just yawning a lot. As we go through all of these different types of molecules, we're going to discuss their physical properties, boiling point, and solubility. Might be good to keep all of that information on another table or another page in your notes or something like that. Just so you know, okay, alcohols have a very high boiling point. Alkanes and alkenes have a very low boiling point. Things like that. Well, we're almost done. Oh, here's a picture of hydrogen bonding in action. So as you can see, remember hydrogen bonding is when I point the H at the electron pair of an NO or an F. And my H is also attached to an NO or an F. So here's my hydrogen bond between these two groups. All right. Now, solubility for alcohols depends on the number of carbons. So if the number of carbons is small, then we give it this term, miscible. Miscible means that it will dissolve into an aqueous solution. Now, the number of carbons where this starts to fall apart is around 4 or 5. 3 or 4, okay. So, for example, butanol, which has 4 carbons, dissolves, but pentanol does not. However, if we put a second OH group on there, it does dissolve. So this does dissolve in water. So each OH group lets 3 or 4 carbons worth of hydrocarbon chain be soluble. Now, your body knows this and is aware of it. So what your liver tries to do when it gets compounds that it doesn't want in your body is it tries to put OHs on everything. And so if you get a bunch of hydrocarbons in your body that are waste products, or maybe you've been poisoned or something like that, what your liver's purpose is to hydroxylate everything it can. And if it puts, I don't know, let's say you had, I don't know, this molecule in you. This is insoluble. And so this would be very difficult to excrete through your urine. So what your body will try and do is it will try and just do this to it. Okay, I'm going to put an OH on it. Well, this is still insoluble, so it's going to put more OHs on it. This is probably still insoluble. This is much more likely to be soluble. And so at this point, your body could just shove it into the bloodstream. It will eventually get filtered out by your kidneys and pass through your urine, provided that this product itself is not dangerous, which is a possibility since your liver is just randomly hydroxylating everything. It has an enzyme that can do that. That is unfortunately as much biochemistry about the liver that I know. All right. Any alcohol that does not have enough OH groups to dissolve all of the carbons into an aqueous solution, we're going to call it immiscible. So 1-pentanol would be immiscible, whereas the other two solutions, 1-butanol and 1,2-pentanediol, these would be miscible. And so miscible and immiscible are basically just other terms to say, oh, it's soluble, when both of the compounds that we're looking at are liquid. All right. And there we go. That's all we're going to do today. Miscible. M-I-S-C-I-B-L-E. Not miso as in miso soup. So, miscible. I don't know if you actually pronounce the C in miscible. I never have. So, I'm also a pronunciation dunce. So, who knows? All right. Remember in the last chapter where we talked about all the different things you could do to alkenes and alkynes? So you could hydrogenate them, and you could halogenate them, and you could HX them, and then you could do all sorts of stuff. Guess what we're going to do with alcohols? We're going to do all of that stuff too. And it's going to be great tomorrow. Thanks for coming out to today's lecture. The quiz for Chapter 13 will be posted right after this class period ends. I'll go and unlock it because we have finished that chapter. It'll be another 15-point quiz. It'll be just like the quiz that you took for Unit 12. You get a week to do it. The quiz results will be released next week after the quiz. And then you have lab worksheet number 2, which the video should now be visible. Hopefully. If it's not, let me know. I will try and tinker with it. It wasn't around yesterday, but I'm sure that YouTube is finished processing it by now. Let me know if it's not there. Have a wonderful rest of your day, and I will see you tomorrow for some more fun with alcohols. Enjoy.